Alright, I think that's probably uh, at least a decent start. So we may as well get started. Uh, Welcome to tree algorithms and everything associated with trees. Uh, so today we're going to go over um, a couple of different concepts. So first of all, we're going to look at trees in general. So what are trees and what are trees as problems? So typically in a lot of competitive programming, one of the data structures that you get presented with, or one of the special cases of graphs that you get presented with, is a tree. And so there's a lot of unique properties about trees that are important to cover. Then the sort of second part of the talk is we're going to talk about trees that we create ourselves to solve very specific problems. And a property that you'll see coming up again and again is the ability for trees to solve recurring problems with logarithmic complexity. And finally, depending on how much time we get at the end, I also want to tackle the lowest common ancestor problem because it nicely incorporates a lot of these concepts in one, as well as being a tree problem. Okay, so first of all, I guess, what is a tree? Well, a tree is a connected acyclic graph. But what's really unique about a tree is that it is two really critical properties. So it's the only way that you can make a fully connected graph that's acyclic. Otherwise, you'll end up with multiple graphs. If you have n nodes and n take one edges, you'll end up with multiple graphs if they're not if you try and connect n nodes with n take one edges and it doesn't end up in the form of the tree, it'll be because you've created multiple graphs rather than you've ended up with you've ended up with a different data structure that somehow, oh sorry, not data structure, a different graph that somehow doesn't correspond to these rules. So, what does this mean? Well, it means that it unlocks a number of properties which we look to exploit, both in how we traverse trees as well as how we treat them in certain problems. So some other unique properties, if you add any undirected edge to a tree, it will create a cycle, because it is the only way to have an undirected graph that is acyclic. And for every two nodes within a graph, there exists a unique path. There exists a unique traversal from one to another, which isn't to say that there aren't ways that we can split that into solving overlapping subproblems, but we'll talk about that in a bit. So I guess first, what is a tree? Well, when we talk about trees, it's often useful to describe it as a rooted graph. So we choose one arbitrary node and call it the root. So this is really useful for implementation, but it's also useful to demonstrate concepts. So if a tree is a DAG, it must have a root, and that root will be the first node in its topological sort. So the roots for this tree we'll select to be node 1. From this root, we then label the nodes that come out from the root as the children of that node. And the root is the parent node in that case. And then as we progress down the tree in a BFS-like manner, or even in a DFS, but with a different kind of meaning, we say that for every parent node, for every child node, there exists a parent node, except for at the root. So in this case, we'll label the root as the parent node, and roots 2, 3, and 4 will be the children of that one parent node. Finally, the last interesting feature about, interesting name for parts of the tree are leaf nodes. So I'm actually in the way here, so I'll remove myself. But you see there's two nodes that do not have uh, any children. So they have less than or equal to 1 edges on yeah by themselves. So these are termed leaf nodes, and they have no children. So trees are very easy to traverse. There's a number of different interesting traversals you can create with trees that we'll dig into a little bit later, especially for speeding up some implementations. But um, it's the same as any other graph where DFS and BFS are all are ways of traversing every node. However, we also have a nice property where because there's no cycles, we only ever have one node to keep track of in our BFS DFS, which is the parent of the previous node. So these examples of DFS and BFS, we've rooted one node called start, and we're then checking to see whether or not the next node in our DFS or BFS we're going over the adjacency list of the node and checking whether or not one of those nodes is the parent. And if it is the parent, then we don't search that node, but we'll search every other node in its adjacency list. Because by the nature of the tree, the only connection that we haven't visited yet, the only connection that we would have visited is the parent of that node. Cool. So we'll move on to our first real property of trees, which is kind of different to many other graphs. So this is the idea of tree diameter. So what diameter is it describes the maximum length of a path between two nodes. So if you imagine doing this on a cyclic graph, this wouldn't really be able to be possible, as there will be a maximum length to reach something, but there's a much larger traversal that's possible to the point that it actually goes to infinity. So this is a property that's unique to trees for undirected graphs, at least. So tree diameter is the maximum length of a path between two nodes. And what that basically means is if we have some tree, let's say that, I'll just draw a very simplistic tree. So the diameter of this tree would be the longest traversal between two nodes, which in this case would be the traversal between 4 and 6, which is 1, 2, 3, 4, 5. So the diameter of this tree is 5. Cool. So naively, we can compute tree diameter by looking at every single traversal possible on the tree. So there's n nodes, and if we iterate over every n pair of nodes, then we'll find that we have, and then we traverse between every n pair of nodes, we'll find that the complexity of this would be O of n squared, O of n cubed. This can be brought down with dynamic programming to O of n squared, but we can do even better than this. So what I'm going to propose is a fairly interesting algorithm, which doesn't necessarily seem intuitive at first. So what I'm going to do is I'll pick any arbitrary node on the tree. I will then DFS or BFS to the node that is furthest away from that arbitrary node, and I'll select that. I'll then DFS/BFS from that node all the way to the maximum path from that first found node, and that will be my diameter. That's what I'm going to assert. And this assertion will be slightly hand-wavy because the proof for this is a little bit rough. But hopefully I'll be able to present something that's like fairly intuitive. So we'll formalize this a little bit with an illustration. So I'll get rid of my tree. But so what I'm actually doing, if I have a little bit of a, oh sorry, actually I think I have a better way of doing this already prepared. Got excited by my whiteboard. So let's look at why this works. So suppose we have this tree. I'll remove myself for a moment, just so that we can actually see the tree traversal. So I'll select some arbitrary node. In this case, it'll be node 8. I then DFS/BFS all the way down to the furthest node from 8. We actually find that there's multiple. Our path could have been either from 8 to 12 or 8 to 13. So in this case, I'm going to say at this stage that it doesn't really matter, and I'm going to arbitrarily select 12. From 12, we then compute the longest distance to the other node. So we started off by selecting 8, then we select 12 from our search to the furthest node from 8, and then from 12, the furthest node from 12 is actually another 2 nodes, which would be 11 and 10. So the distance between 12 and 10, we're going to select 10 arbitrarily here again, is 6, and our diameter is 6. So this is an example of the algorithm in action. But why does this actually work? What is the reasoning behind all of this? So if we draw out our tree in a way that looks similar to a carbon chain, we can see very quickly why these searches end up netting the largest diameter. And that's purely because from any arbitrary node, we can guarantee that we're going to find an endpoint of the diameter. So regardless of what node you look along there, an endpoint of the diameter will be the furthest node from that point. So for instance, if we look at 9, the furthest node from 9 would either be 10 or 11. If we look at 6, it would again, I believe it would be the case that, no, it would always be 12, yeah, it would always be 12 is the furthest away in that case. But also looking at this, another thing that we can notice is it doesn't really matter which selection we took. Like if we took 13 as the selection and 10, then the diameter would again be the same. And this is also the case with 11. Obviously, this isn't a very rigorous proof, but I hope it identifies the intuition behind why this algorithm actually works. So this is essentially just repeating it, what I just said. So finding the furthest node from any arbitrary node will always find one end of the diameter, and that's the property that we exploit. Cool. I'll come back. So a very common problem for trees is determining what we call the center of a tree. So the center of the tree is the node which minimizes the longest traversal to any other node in the tree. And what that actually means is that if we have some tree, there exists at least one node. It actually can be a node or a pair of nodes, where the sum of all traversals from that node to, not sum all, the maximum of all traversals from that node to every other node is at its minimum. So keeping that in mind, intuitively, a way of thinking about this is to look at minimizing the longest path. Because if we minimize the longest path, then uh, it would make sense that we've minimized every path in the tree, or every like traversal in the tree. So if we minimize our traversal of the diameter, which we define as which we know is our longest path, it then seems to follow that we'd be able to minimize our overall maximum, which is a reasonable intuition, and it does actually turn out to be correct. So to talk about this in a little bit more detail, I'm going to define another algorithm. So I'm going to consider another way of finding this center. So if we have some tree, such that I'll again draw it out. It'll be a little bit more complicated a tree, so we'll have around about 10 nodes, just so that it's not trivial to find the center. And they'll just be grouped around. So remember, what makes a tree is there are no cycles, everything's connected, and there is exactly a unique path from any one node to any other. So I believe that's a fully... Oh no, sorry, I've got an extra edge. So that will be a valid tree. And what I want to do with this tree is say if I take away any edge at this point, that I'm going to have a center still. The center is still going to be the same. And the intuition behind this is that if we defined our center as something that minimizes all the maximum paths, so all the maximum traversals, and we know that removing leaf nodes will guarantee that we're decreasing our maximum traversal by exactly 1, because a maximum traversal must end at a leaf node, then we know that if everything decreases by 1, that our center will stay in the same place. So a great way to find where that center is to look at the step before the entire tree would be erased, and like that would be our center. So this could either be a pair of nodes, or it could also be a single node, depending on, well, we'll see what it depends on. So in this case, let's look at what leaf nodes exist. So 6 is a leaf node, so we'll erase that. 5 is a leaf node, we'll erase that. 10 is a leaf node, we'll erase that. 4 was actually connected to, I believe it was 5, so we'll leave that for now. 9 is a leaf node, and 7 is a leaf node. So this is our first pass, and you can already see in this case we had a fairly small tree, so a dramatic amount of it has been removed. But remember that every maximum traversal that remains at least was only decreased by 1. So every maximum traversal still exists, or the maximum traversal still exists. So we'll again do a second pass to find out, to remove leaf nodes. So in this case, 8 would be a leaf node. 4 would be a leaf node. And finally, in our last pass, we'd remove 1 and 2. Oh, sorry. Yeah, 1 and 2. And we find that 3 is our center node. So this algorithm is provably correct, as well as makes sense. And hopefully it'll lead us to understanding a little bit more about the diameter algorithm. Oh, sorry, the original diameter, the original way of finding center from diameter that I was talking about. Okay, so So this is essentially explaining the algorithm where we're taking away a leaf node every time, um, and this will decrease the maximum traversal by 1 each pass. So how does this relate to diameter? Again, we just recall that the endpoint of a diameter must be the end of a search. Hence, it must have exactly one edge, which means that it is a leaf node. So the idea behind that, I think I glossed over that maybe in a little bit too much detail. Sorry, too little detail. If we recall that when we're DFSing or BFSing, the only node that we've visited in the past will be the parent of the node. So if a search is unable to progress, it means that the only connection to that node is the parent. And that's the case where something is a leaf node. So we know that because our diameter is the end of a search, it must be a leaf node. Cool. So now that we know that, actually I'll move myself out of the way for this text a little bit. All we need to do is show that after each pass of the algorithm, that the nodes in the pass of the previous diameter form the diameter of the new tree, and we prove the lemma. So a nice way of thinking about this is through thinking about the opposite. So what if this wasn't the case? What if it was the case that we could somehow remove all the leaf nodes from a tree and it would end up with a different diameter? So, a path that had a diameter that was larger than the previous diameter that we had. It's okay if we have a path that has the same diameter, because naturally, as we remove nodes, we're going to eventually remove enough nodes that it'll get to the center. If we have two the same diameter, but maybe I've hand waved that a little bit, and I can explain that in a little bit more detail. But yeah, we basically don't care if there are two diameter parts or two or more diameter parts existing, but we do care if somehow after this transformation the diameter changes so that it can't possibly be the previous one. So for that, we'll call a diameter d. So in order to find this case where the next d would actually be larger than the current d, we know that both ends of the diameter will be leaf nodes by definition. So we have to somehow find a path that either had one of three cases. So either it was made up of no leaf nodes, and it had size of d take 1, or we have a path that's made up of one leaf node, and it had size of d. Or we again find another node which we find another path that had two leaf nodes but had value d plus 1. So we can find that none of these are actually possible due to how the definition of a diameter works. So let's talk about each case in detail. So what was labeled on the text was there are two values I'm going to define. So d is the diameter before the transformation. And then d prime is diameter after the transformation. So the cases that I need to find, I can express this in either d or d prime. But basically, by definition, d prime equals d take 2. So I need to find cases where I can find a path that after the transformation must have size at least d prime. I need to find some path. So I'm going to call this like length of path. So len of path greater than or equal to d prime plus 1. So I could do this technically as well, but it makes more obvious that the path must be integral if I do greater than or equal to d prime plus 1. And it also lends nicely into my 3 cases. So in order for this to be the case, we have one of 3 options. So either so with every transformation, we're removing leaf nodes. So we can either remove up to 2 leaf nodes from a path, and we can also remove no leaf nodes from a path as our minimum. So we have the case of removing no nodes, removing 1 node, or removing 2 nodes. And we know that we remove a node if it's a leaf node. So if we draw out our 3 cases, that means we find either we have to have a path that after the transformation, so say we have, first of all, path with 0 leaf nodes prior to the transformation. Alright, so this would require it to have exactly so for a path with 0 leaf nodes prior to the transformation, to have d prime plus 1 length, it would require the existence of 2 more leaf nodes that would come off this path, because it can't have any leaf nodes in order to have this happen. So we guarantee that we're going to have at least 1 extra node on either end of the path, at least, which in this case means that our size before it must have been d plus 1, which leads to a contradiction for this case, because if there was a path with d plus 1, it would have been the diameter, but it wasn't prior. So this can't exist. Alright, cool. So that's path with 0 leaf nodes done. We'll see a similar case for with 1 leaf node. Prior to transform. So if it has 1 leaf node, then it again must reduce down to d prime plus 1. So its amounts before the transformation must have been length d, in which case it's already a diameter. So if it's already a diameter, then it must have already been a diameter, but it somehow had a leaf node attached to it. Sorry, it somehow didn't have a leaf node on one of the ends, which means it can't exist, because there must then exist a diameter with d plus 1, which would have been the actual diameter. So it leads to another contradiction. And we'll see the exact same line of logic being used for if it has 2 leaf nodes, because it would again be the diameter, and it would have had to have value d plus 1 for that diameter. So because of that lengthy way of going about things, we know that every single time this transformation happens, we're going to end up with the diameter. And so when we finally remove all the nodes from the tree, up until we're about to remove all of them, so the step before it, we're going to continue to have the diameter. So the center node will be the center of the diameter, whether that be one or two nodes. Cool. And this is pretty much saying that again, I believe. Yeah. So we now have two algorithms to find the center, if we want to go about that. So either we have the algorithm to find it by looking at every single leaf node and removing it until we're about to erase the tree, and we would store that result. Or it's going to be to find the diameter with the two searches that I talked about before, and then taking the middle node on that path. So if you want to speed it up and not do three searches, you can technically do a laggy pointer in the second search, and so you only need two searches rather than having to traverse the path to find the diameter or to store that path. Cool. All right. So another property of a tree is its centroid. So what is a centroid? A centroid is basically a node that splits a tree into two equal parts. So what that means is, say we had some tree. Again, I'll draw a slightly more complicated tree just so that the example isn't trivial. 8, 9, 10, and we'll connect everything. Yeah, everything's connected. Cool. So the centroid is going to be a node where once you remove that node, every single subtree that's created will have no more than n on 2 elements. And this will exist for at most 2 nodes in a tree. So in this case of the tree, it's a little bit obvious. So we have 10 nodes, as I've labeled them 1 to 10. If we look at the node at number 9, just visually at least, we can see that it splits the tree into size subtree 3, subtree 2, subtree 1, and subtree 3. And none of those are at least 5. And so that's going to be the centroid of our tree. Now that was obviously just by looking at the tree, but there's a better way to go about it. There's an actual way to go about it, which we can formalize. Cool. Oh, and another point on centroids, they're very important for a technique of trees where you create a decomposition of the tree called a centroid decomposition, and it's useful for answering specific queries in of log. I've got log v there. It's technically log n because trees have n vertices and n take 1 edges, so it's approximately O of n for anything. For any anything with vertices. So we won't be covering this today. There's also another decomposition which does a slightly different thing what I like as a better way, called heavy light decomposition. But yeah, the idea of both decompositions is to answer specific queries in log n time, and they're queries on trees. They're not queries on most normal data structures. So yeah, we won't have time to cover this today. Cool. So how do we go about finding the centroid? So let's formalize this a little bit. So we know the centroid exists where every subtree has greater than or equal to n on 2 nodes. So, that's the wrong way around, where every subtree has less than or equal to n on 2 nodes. So if we know the number of nodes in each subtree, computing the centroid is trivial because it's just a matter of going through every node until we find the node that has that satisfies our search. If you want to speed this up slightly, then we can actually go to, we know that the node for our centroid is going to be located in wherever we have the biggest subtree of where we're searching. So let's pick an arbitrary node and we'll step through this algorithm. So if I pick, if I pick node 7 and I want to step through this algorithm, I'd see that the subtree it would create is just one of size 9 and it has no other connections. So I'm forced to go into this subtree. Now I traverse from 5. So 5 splits it into a subtree size 8 and of 1, and 8 obviously does not hold for the search. So we go another layer deeper. So into our 8 node. At our 8 node, we find that it splits it into size 2 and size 7. Oh, sorry, I've actually rubbed out a bunch of stuff with that. Yeah, so size 2 and size 7. Again, this isn't adequate, so we move on to 9, and we find that it splits it into subtrees that are less than or equal to L on 2. Cool. So that's basically the naive, oh sorry, not naive, this is the trivial way of looking at things. So what's the catch here? Why can't we just do this normally? So it's the idea of we have to actually find out what the subtree values are. So if we can somehow compute what each of the subtrees will be underneath that will get split into in constant time, then we have a linear time solution, which will just be going through every node to figure out which one is our node that we want. So this is suspiciously, we're calculating depth on a graph. This sounds suspiciously like DFS, and it turns out that DFS is a very good way of doing this. I think I have a slide missing. I think I do. I'm not sure where the slide went, but okay. So basically, the only other thing I have to say about centroids is that so if we DFS along from any arbitrary node, so let's root node 5, and we do a DFS along it to calculate the depth at every tree. We can then say that for any child, so a child will have like a certain depth. Let's say this child here will have depth of 3. Sorry. So I'm calculating height here with my DFS. So what it would look like is I would go all the way to the bottom of the tree and say, all right, your height 0. Then its parents are height 1. Its grandparents height 2. So on until we get all the way back up to the root. And for computing the size of each, computing the depth of each subtree, so like, apologies for that. If I'm at this node here, I have I know the total number of nodes, and I know the subtree size here, and I know my value of my subtree. So the value of my parent's subtree, which all I know is like its value will be the size of this subtree. I know that the value of this will be I know the value of like this large subtree for the parent will be the total number of nodes uh, take the subtree at my node. So because of that, we can we can go to any single node within this tree, and we can compute the depth at any point. Oh, sorry, not just the depth, but the size of every subtree beneath it. And that makes our algorithm fairly trivial. And that's all I have to say on Trees' problems. We might go a little bit over time to talk about Trees' data structures themselves, but I'll try and speed through it as best as I can. So trees are cool and all, but can we make our own? And how useful would they be? So typically trees are going to be used to turn problems that have recurring necessities, like recurring problems that are similar to solve. It makes it so that instead of taking linear time, it'll take logarithmic time. That's essentially what a tree tries to do. Cool. So the first type of tree I'll talk about is a binary tree. It's pretty straightforward. So there's a single node that we designate as its root. And every node can have up to 3 edges. So its 3 edges would be the parent, left child, and right child. It can have no more than that, but it can have less. So it can have no parent, which is the case of the root. It can have no left child, and it can have no right child. It's not bound to have either no children or fully populated. Otherwise, it would be impossible to represent some things as binary trees. Cool. So if we extend this idea of binary trees to make some sort of order, we end up with a data structure called a binary search tree. So the idea of a binary search tree is it's a binary tree where it stores keys, and those keys have a comparative value. So for instance, if I wanted to store numbers in a binary search tree, the numbers that would be less than the node that I'm at would go into the left child, or I'd traverse into the left child to find where I was trying to insert my data or try and search for my data. And if it's greater than or equal to, then I would traverse into the right child. So it doesn't necessarily need to be the case that greater than or equal to nets the idea of, it doesn't necessarily need to be the case that you handle duplicates by traversing into the right subtree. It's just the case that with a lot of comparable functions, they're based on the less than operator. And so the strictly less than operator will return false for greater than or equal to. So that's the convention that I personally typically use when handling duplicates. But the only formal definition is that your left subtree will be less than, the keys in the left are going to be at least less than the keys at the current position. And similarly, the keys in the right child are going to be at least greater than the keys in the current node that we're looking at. Cool. So on first glance, before we talk about that, I'll just go through a couple of special traversals. So these traversals come up typically during coding interviews. You don't normally see them much during contests, but it is good to know them, and it's good to have a decent idea of how they work. So I'll just quickly skim through them. So I'll draw a binary tree. a binary search tree in this case. It doesn't. So all these traversals don't necessarily need to take place on binary search trees. They work for any binary tree, but particularly for in order, it makes a lot more sense to view it as a binary tree, a binary search tree. So we'll start with node 5, or sorry, a node with key of 5. You can have 3 to its left, 4 to its right, 4 to the right of 3, 2, 1, and this can have 8, 7, 6, 9, 10. Cool. So this is an example of a binary search tree. And all these traversals are special ways of visiting nodes in this tree. So we'll start with what pre-order looks like. Oh, sorry, no, what in-order looks like. So in-order is quite easy to consider with binary trees, binary search trees in particular, because the definition, by definition, if you do an in-order traversal, you'll end up with keys in the sorted order, as long as it's a valid binary search tree. So the algorithm that we use to do that is we visit the left node, then the root, then the right node. Then the right. So how it will look generalized is we visit the left node, which is going to be 1. Then we visit the root, which will be 2. There's no right, so we again visit the root. And we write that down, so it'll be set 2, 3. I'm not going to write all of this down, but I'll step through enough to generalize it. We then go to the right. There's no left, so we write 4. We then go to the root, which is 5, because we already covered 3. And we write down 5. Then we go to the right, and we go all the way to the bottom, because we want to visit the left first as our first priority. So going as far left as possible when on a subtree is ideal. Then we go to the root, which is 7. Obviously the root, so a good way to think of it is if your priority is left, left, root, right, at every single node that you look at, you want to go left. And if it's not possible, then you go to the root. So for 6, it's not possible to go to the left, so we go to 7. At 7, it's not possible to go to the left, so we write it down, we go to 8. At 8, it's not possible to go to the left, it's not possible, so we write the root. Again at 8, it's not possible to go to the left or to write the root, so we go right. And then we write 9. It's not possible to go left or to the, it's not possible to go left or to the root, so we write, so we go to the right and we write 10. And so that's how we end up with our in-order traversal. And the exact same ideas apply to all the other traversals. It's just the order of which you visit nodes changes. The only special traversal where this doesn't happen is the level order traversal, and the level order traversal is just a BFS. So we go left to right from top to bottom. So level order would look like 5. Oh god, that's a strange 5. 5, 3, 8, 2, 4, 7, etc. Cool. And the other couple of searches that are on here are just different orderings of the in order. But it's the same idea of the way that you prioritize nodes. This is the missing slide. So this is just talking about the centroid. I don't know how that got mixed up. Okay, so go back to binary trees. I'll reorder those slides later. So binary trees look really cool at a glance. We can store the height of our tree is going to affect our search. So we can typically store things in storing something in a binary tree uh, from a randomized set of values will be average time of log n, because uh, we store up to 2 to the n elements, um, and yeah, it's the proof of this is actually kind of hard, but the average time is log of n. Um, and the average time for insert is also log of n. Intuitively, just from the height of the tree being our insert time, and on average, it's going to end up with this kind of. There's going to be some longer branches than others, but it'll average out to around about log n. So it appears like it's a superior version of a sorted array with binary search, because sorted array with binary search, although it supports log n query, and it's n log n to create, it actually costs O of n to insert, because not only do you need to insert a value, which takes the binary search probe. Once you do, you need to bump every value one along in the array. So it's O of n to actually insert. So it looks like we've discovered a better version of that. However, there is a catch. There is a worst case for binary trees. So for particular data entries, particularly in reverse order or in order, or in sorted order, sorry, we find that our insertion nets us essentially just a linked list, which which means that our searches will be linear, our inserts will be linear, and yeah, nothing, everything is fairly awful. So we talked about before that the reason why insertions and searches or queries in general were logarithmic was because of the height of the tree, and now the height of the tree is linear, so it's no longer logarithmic. What's the solution to this? Well, how would we just make the tree shorter? If we enforce the height to be minimum, we can guarantee that our solution will be worst time logarithmic. This doesn't necessarily mean that it'll be the best case running time, but yeah, it'll be logarithmic time. So this data structure is called a balanced binary search tree, because in order to keep the height at a minimum, we don't want to have very long lines of nodes. And all of these popular ways of doing this, except for a splay tree, aim to minimize height in some way. So the splay tree is a little bit different, because the way it actually works is by rebalancing based on the most recent queries. So you can actually end up with a splay tree that looks a lot like a linked list. But the reason is because all the nodes that want to be accessed, there's only like 4 queries that get done constantly, and so it needs that constant time. Alright. So yeah, I won't really talk about implementation of all of these, but the idea behind all of them is to reduce the query time through rebalancing in a certain way. And that rebalance is done through a rotation. It'll be possible to rebalance in n log n time naively by just reconstructing the whole tree. But let's say I have my awful case for insertion where 1, 2, 3, 4, 5. What I'll do is call a function rotate on a node in order to rebalance this. So if I call rotate on 4, what will happen is this node will get moved up and bump out the tree beneath it. Sorry, the tree where the parent was, and then I'll move to be its new subtree. So for instance, we have one. So after a rotation here, it would become 1, 2, 4, 3, 5. And in this case, we've now, our height of our tree is now 1 less. And so you can see if we keep on rebalancing, we can get to the optimal, the optimal height. Cool. So yeah, we're very fortunate in C++ that all of this is pretty much implemented for us already. There's only it's only pretty much if you need to add augmentations to these kind of data structures that you can't just use the ones in the standard library. So standard set and standard map are implemented as red-black trees, and GNU policy-based data structures are also red-black trees, but they allow ordinal searching. So it returns the order of a key or finds the key with a certain order, which is quite important for, which is pretty much the way, allows binary search on a tree. So it fully incorporates the idea of just a better sorted array with a binary search. Cool. So it looks like we're not going to have a huge amount of time, so I'm just going to tackle segment trees as probably the last topic. I did want to cover lowest common ancestor, but it doesn't look like we're going to have time because segment trees are a little bit time consuming. Okay, so we did cover segment trees before in the divide and conquer session, but we didn't cover it in a huge amount of detail because I had to go through it quite quickly. So I'm going to try and go through it in a lot more depth and sort of derive a way to get to the data structure or the implementation that I was talking about in the session. So first of all, what is a segment tree? So we recall that a segment tree is basically something that it's a data structure that solves range query problems. So if we want to do some operation over a range on a list, then we'd use a segment tree, because a segment tree would be able to do this once it's constructed. Any successive query could be done in log n time. This is also possible to be done in constant time with difference arrays for some operations, but it's not possible to have difference arrays be able to update in log n time. So a common theme about trees that you've probably been seeing throughout the session is that the main idea is that everything about a tree is logarithmic. There's no linearity, or very little. The only linearity is typically with building the tree, because it has to read in the number of elements. Yeah, so its update is log n, its query is log n, and to build this, because there's exactly n take 1 nodes, actually sorry, that's a white lie. We'll say that there's exactly 2n nodes, which is not necessarily the case. We can compute up to 2n nodes. So our upper bound at least will be 2n, which means that our time complexity will be O of n. And I'll explain how we get to that a little bit later on. Okay, great. It's a logarithmic data structure, but what is it? It's not just magic, it actually exists. So I think the best way to talk about this is through an example. So I'm going to create a segment tree with 30 elements, and it's going to compute the sum over a range inclusive of the lower bound and exclusive of the upper bound. So I'm using this because it leads to very nice implementation. But if you're having to do a segment tree with different areas of these bounds, whether you have to be exclusive of the lower bound or inclusive of the upper bounds, it's very easy to mutate the bounds before actually putting it into the query. Cool. So exactly how can we do a sum over a range provided by two indices? Well, if you recall from divide and conquer, the idea was always to split our problem into partial problems that we can solve quickly. So how about we rewrite the sum over any two indices as the sum of partial sums with increasing binary intervals. That way, if there's increasing binary intervals, we'll never have to store more than 2 times n increasing values. But we can guarantee that we can write any range as the sum of any two values. How is that possible? Well, I think, again, it's probably best... actually, sorry, I'm skipping a little bit ahead. We'll talk about the actual data structure first. Okay, so let's create a forest of binary trees that represent these partial sums, or these partial binary sums, binarily increasing sums. So if we have a list with 6 elements, then our forest of binary trees will look like this, where we can represent any sum between any two indices with values from these nodes. So quite obviously, this would be the case if we were just traversing along the bottom level, but it's also possible to go up a level each time and traverse any queries. Cool. Oh, sorry, I should clarify, just before, because we go up a level each time, it doesn't mean we necessarily take an addition from that level. And we'll talk about that in a little bit. Cool. So let's talk about the partial sum. So what would these partial sums actually look like? Well, the idea behind these partial sums is that we want to get to a point where the range in our data structure is like maximized. So what do I mean by that? Basically, we want to it's best shown with an example. Okay, so for example, I'm going to talk about the one on the board. So if we're trying to find the sum from 11 to 30, not inclusive of 30, that's going to be the same as, well, we can first of all pull out like a solid divide that we want. So we're supposed to represent this as a sum of partial binary sums. So it's really important that we're splitting this by values that are with the lowest, with the greatest least significant bit. Why is this important? Well, if we go back to our tree previously, we can see that on each level, the interval for, the lower bounds of the interval will have, will determine what's the greatest level of the tree that will reach. So for instance, 0 is an edge case, but for 4, if we continued that tree, I'll actually draw out a slightly bigger tree. Oh, sorry. Actually, is that right? Yeah, okay. So if I draw out a bigger tree than the 6 that we have, if I draw out a tree with size 10 elements, so it'll be from 0 to 1, 1 to 2. Actually, I won't draw the brackets because it'll get a bit tedious. 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. So this is our 10 element segment tree. So each of these trees that I create in the forest will have a maximum depth that's determined by the lower bound of this interval. And similarly, when we look at the right bound, it'll also have a determination. But we'll talk about that in a little bit. So, so for the case of 0, 0 does not have a least significant bit. So we treat it as the infinity case. So there is no matter what, no matter how many elements you start with, 0 can always be represented by the top element. So the restricting element will be the right bound rather than 0 in any way. So so when we look at something a little bit different, let's look at 2, for instance. So 2 has the least significant bit of 1, which means that when it gets up the tree, you can see that it no longer has another representation. It no longer has another interval. So this interval will be inclusive of 2, exclusive of 4. So it will be from 0 to 2. And this will be from 0 to 4. So you can see 2 disappears, 2 falls off. So, so because of that, when we're computing a range between two values, let's say that we're trying to compute the range 2, 3. Oh, sorry, I've actually drawn the brackets the wrong way. And I didn't even want to draw 2, 3. I want to draw, so from 2, which is here, inclusive, to 9 exclusive, which is here. So if I want to draw, if I want to calculate that bound, I first of all look to partition this by the maximum like part of my array that's going to be the part of my tree that's going to be within that range, which is going to be given by the number with the greatest least significant bit. So let's do that partition. We can see between 2 and 9, the number with the greatest least significant bit is going to be 4. So this is going to be 4 to 8 here. So the least significant bit of this will be 4. So we're going to rewrite this as from 2 to 4, and then plus from 4 to 9. And then we can, so we know 2 to the 4 is already in the tree, so we're done. 4 to 9 is not in the tree though. So we look at the next best thing, which is 4 to 8. So this we'd replace this as plus 4 to 8 plus 8 to 9. And that's how this decomposition works. We're finding this peak point, and we're looking at each side calculating the bits that are remaining, essentially. Cool. So let's formalize this a little bit. So this is a slightly more tedious example, but it does the same thing. So how do we actually implement this? So let's think about the decomposition first. So every beginning index has a maximum range within the data structure. So this value with the least significant bit is going to be like when we reach it, and its range extends past where we need to get to. So we basically want to take a left bound and keep on increasing it by the greatest range that'll let you increase it until it gets to that point where increasing it will move past the right bound. And we know at that point that we've found our largest number with the our number with the largest least significant bit, which will be our peak in the partial sum. And similarly, we use the same rule from the right to get to that, to do that other part of the sum. And so if we save the results for each of those values, then suddenly we have our final computed answer. So I'll move away from this a little bit. But yeah, basically, this is an implementation of exactly that. So if we first of all traverse along, I'll see if my mouse shows, but if we traverse, so first of all, we look at the edge case of if L is 0. So if L is 0, then we assume that it's infinity. So we already know that its max range will be past it. It looks like my cursor doesn't show, unfortunately. See if I can get a pointer. Yeah. Okay. So yeah. So if L is greater than 0, then it'll go into this loop. So if it is 0, there's no point. But yeah, so we compute first of all whether that maximum range, which is determined by its least significant bit, is within the bound. And if it is, then we add that interval's bound to our running total. And we compute the new bound of the interval as the right side of that interval that we did. So this implementation uses like some random data structure where we can pull out a constant time value for that interval, which in this case we're using as a hash map. But this can get this is a little bit bad because it's possible for hash maps to be non-deterministic and have worst case running time of O n squared. So this is a good way that we can get constant time. But this is a way that we can simulate constant time to start with, at least. Just as a side note, if we index this differently so that we were using, instead of just this interval, we were using a two-dimensional matrix where one of the indices was the size of the left bound. So the left bound bit shift by whatever level it was on, and the second index was whatever level it was on. Then we'd have a data structure that could actually solve this problem. That's called a sparse table. But we're not dealing with this at this stage. Also, sparse tables have longer compute times. Alright, cool. So how do we actually now implement something that that indexes this correctly without using a hash map? So the easiest way to think about this first is to actually build the segment tree. So this is our method to build the segment tree. All we're doing in this method is we're populating first of all an array with zeros. It doesn't matter what we populate it with. We don't care because we guarantee that we're going to first of all insert all of our values into the end of the array and then compute our parent nodes based on every pair of adjacent nodes. So this will leave us with some don't care values, but we guarantee that as long as we're always our algorithms are acting in a way that they're always accessing legal ranges, that we'll never run into these don't care values. So that's essentially what this is saying. Cool. So now with this data structure, all we need to do is find a way to index our we need to index our hash map. We need to index this data structure with the interval that we wanted before. So we know our interval will always be made up of some L and R such that L has least significant bit that's greater than or equal to the current level that it's on. And the distance between L and R, so the interval, will always be equivalent to 2 to the level that it's on, or 2 bit shift by the logarithm of R take L. So all of that text is essentially saying why this is the case. But if you can think about it as, all right, on every level, we're increasing our interval by 2, then this makes sense as we're trying to move up the tree as we're creating larger and larger intervals. Okay, so if we now have this formula for our converting our interval from the interval L to R to an actual physical number for our index, we can now implement a segment tree. And that is this. This awful looking bit of code is a segment tree implemented. Luckily, we don't have to do something like this. We can make this function quite a lot simpler. But this does work. This is technically a segment tree. Just using that idea that our interval that we were using before is now serialized as an actual index. So this all works, but it's a little scary. And there is an easier way to go about this. So instead of using the LSB, we're going to bit shift both L and R. And what that bit shift will do is it'll move it up a layer of the tree. So when an indice, so we cared about the LSB when we were calculating whether or not to add a value. So now we're only going to add values when they reach their LSB. Because at that point we've already we figured out that they're supposed to belong to the tree, or they're supposed to belong to the sum. So their LSB will be when they are an odd number, because that's when they've reached their least significant bit. So we've already computed the index for the tree for the left, and our right tree's index just becomes R take 1. And that's because if you look in the previous slide, and we have a look at how we were calculating the index for R, we actually do R take 1 bit shift LSB to the R, and then bit shift it back. So this plus n is like how we start things off. So this will just be R plus n, bit shift however much by this LSB, take 1, because the bit shifts cancel, which is useful. Apologies. All right. So what does this implementation look like? It's far cleaner, far cleaner. So all we're doing here is checking for when it's at its LSB, which we're doing by checking if it's odd, and if it is, then we add it to our running total before bit shifting each time and returning. And Python, this looks a little bit longer, but there's an even nicer implementation in C++. That's pretty much. Oh, sorry, yeah. We sort of glossed over the update function because the update function is not very exciting. All the update function says is basically, all right, we're inserting a value at an index. So we'll first of all put that value into the segment tree because a leaf node will have that value, and then we'll compute every value that had that leaf node as a dependency, which takes log n time. And this is the implementation in C++, which is very, very short and very clean. So if you're ever wondering why segment trees work, this is a really great reference. And the code for this is very short. And with that, I've definitely gone quite a bit over time, unfortunately. So we won't have time to cover a bunch of other stuff, but ideally we'll be doing another session on trees in, I believe, 2 weeks, unless strings runs for multiple sessions. But thank you very much for coming. And